Hello everybody, I'm Raffaele Sommese, a PhD student at University of Twente, and today I'm going to talk to you about DNS delegation inconsistency. This work is a joint collaboration between me, Giovane Moura from SIDN Labs, Mattijs Jonker and Roland Rijswijk from University of Twente, and Alberto Dainotti and Claffy from CAIDA, and Anna Sperotto from University of Twente. First of all, let's introduce the argument. The domain name system, I don't think that we need to present the domain name system, but it's one of the most critical components on the internet today, and it's a high distributed hierarchical database, and the principal role of DNS is to map a host, service, and application to IP address and other various type of records. One of the key elements that enable the hierarchical structure of the DNS is the delegation mechanism. In particular, the DNS is organized in parent and the child zone, typically managed by different entities, and we have different zones that share common information, such as NS records, about which are the authoritative name server for a given domain. So we have this information that is the NS record that is replicated among a parent and child zone. One of the first RFC that defines the DNS as we know today, the RFC in 1034, states that the NS records at both the parent and the child zone should be consistent and remain so. So the purpose of this work is to understand if this is always the case in practice. The contribution that we will provide with this work is to provide a broad characterization of the inconsistency in DNS delegation and to investigate the practical consequences of this inconsistency. Let's first look to a well-configured delegation. In this case, we have an example for example.org. It is a real existent domain, and in .org zone that represents the parent zone in this case, we found the example.org name server record that points to a.yanaserver.net. That is the authoritative name server for this example.org domain. In the child zone, a.yanaserver.net, we found the same information with the same configuration for NS record. So we have the same NS record both in the parent and in the child zone, and this is a well-configured delegation. What we discovered is that we studied the delegation consistency between parent and the child zone for all active second-level domains for .com, .net, and .org, and we analyzed more than 166 million domain names, more than 50% of the DNS namespace. 80% of these domains exhibit consistency, but 8%, around 13 million of domains, do not. The remaining 12% of the domain are domains that are not resolvable in our system. So we try to categorize this kind of inconsistency. We try to divide this kind of inconsistency in different set of inconsistency. We found 4 sets of inconsistency. The first one is when the parent and child have a completely disjoint NSSET. The second is when parent NSSET is a subset of the children NSSET. The third is when parent NSSET is a superset of the children NSSET. And the fourth category we call the rest category. It's a parent and children NSSET have common elements and some different elements. Some common elements and some different elements. In 55% of domains with delegation inconsistency, parent and child that we found parent and child as disjoint set. Let's look at an example of disjoint sets. Let's take back the example of example.org. In this case, if example.com .org has a disjoint NS set, what we found is that in the parent we found a.yanaserver.net, while in a.yana.server.net we found c.yanaserver.net as NS record. In this case, the delegation is inconsistent, and the delegation in the parent is completely different from the delegation in the child. What we discovered that of these 55% of domain, half of these at least are consistent at EP level. That means that they point to a different name for the name server record, but these different names points to the same IP address, while half of that, the other half of that half part is not consistent at EP level. That means that points to a different server. We discovered some cases of disjoint NSSET between parent and children also in the root zone. In particular, 16 top-level domain present this kind of inconsistency, but all of them are consistent at EP level. Which are the consequences of the disjoint NSSET? Obviously, different servers, we have different servers defining parent and child. Some of these servers could be lame delegation, so not authoritative for that domain, and this could bring to problem in resolution. Even if the EP level is consistent, as we've seen for 50% of the cases, keep the A record in sync. These different A record in syncs makes the misconfiguration easy, and also the behavior of the resolver is not predictable, because the resolvers can go to the parent or can go to the child NSSET. One real case that we discover in root zone with this kind of disjoint NSSET, it's the Indian EN top-level domain case. In particular, India EN registry as NS1 6 neostar.en as NS record at the parent root zone, and NS1 and NS6 registry.en at the child zone. But both of these NSSET point to the same quadruple A records. We notify them, and they fix this inconsistency, and they fix also 15 other international CCTLDs managed by them. Another case quite common is where the parent NSSET is a subset of the children NSSET. In this case, we have that 30% of domain with delegation inconsistency the parent is a subset of the children, and in 18 top-level domain we have in the root zone we have also this inconsistency. Let's look at the example. In this case, basically we have in the parent we define only A and B.yanaserver.net as authoritative name server, while in the child we define A, B, C, and D. Consequences of this parent subset where the parent is a subset of the children. We have a false sense of redundancy, because basically the name server defined in the children are never queried and never used. So we have less resilience, and the load is not well balanced, because only the name server defined in the parent are used, and not the name server defined in the children. Also in this case we have a real world case, and it's the case of AT&T. AT&T main domain AT&T.com has had a parent NSSET containing NS1, NS3, AT&TDNS.com, whereas the child has NS1, NS4, AT&TDNS.com. We notify AT&T of this misconfiguration. They fixed adding to the parent ns4.attntdns.com. Other case that we classify is when the parent is a NSSET, it's a superset of the children NSSET. In this case, it's 8% of the domains with delegation inconsistency, and 10 TLD in the root zone. And the example is shown there. Basically, we have the example.org with the A, B, C, D, yana.server.net as authoritative server, while in the child we have only A and B. yana.server.net. Which are the impact, the consequences of this parent superset? If the additional name server are unreachable, we have a higher resolution time or random failure in the process of resolution. More risky is if the additional name server defining the parent are dangling. That means that the underlying domain could be registered, so we have the risk of hijacking because a potential attacker can take the control of the domain. The remaining category we define as REST category, it's where we have a sort of mixed behavior. So in parent we have in parent and child we have and children we have some common elements, but we have also some different elements. 7% of the domain with delegation inconsistency, and 8 top-level domain present this kind of inconsistency. And basically all the risks that we mentioned before, all the consequences that we mentioned before, can be applied to this case. We will try also to categorize the impact on the resolver's behavior of this kind of inconsistency. For doing that, we use RIPE Atlas, and we try to measure how the resolution process works when we have a case of inconsistency. In particular, we try to resolve a simple query against a domain that is not well configured, as the 4 case that we showed before, and we try to study the query load in the name server defining parent and the child, setting up all the name servers behind the same network, so we don't have issue in load balancing between name servers in different networks. Before introduce the results of the experiment, let's introduce the difference between minimal responses and normal responses. What we have is that if an authoritative name server is configured with minimal response disabled, so with normal responsive, he provides in the answer in the authoritative section and the additional section information regarding the authoritative name server for a certain domain that we query. Instead, if the server is configured with the minimal response enabled, what we have is that in the answer provided to our query, it's provided only the answer section, not the authoritative and the additional section. As we can see from this slide, if we have a disjoint NSSET, so the name server defining the parent are completely different from the name server defining the child, what we can see is that with minimal response, the resolvers doesn't know at all the existence of name server defining the child and just query the name server provided by the parent. Whereas in case of normal response, they learn through this authoritative section that there are name server defined in the child that are different from the one defined in the parent, and some of them prefer the name server obtained through this authoritative section, so start to query the name server provided by the child. In the case where parent NSSET is a subset of children NSSET, what we have is that NS1 and NS3 it's defined both in the parent and in the child, while NS2 and NS4 is defined only in the child. And in case of minimal response, where the resolver doesn't have any way to know about the existence of NS2 and NS4 because this information is not provided in the authoritative section of the answer, all the queries goes only to the authoritative server defined by the parent, so NS1 and NS3, while in case of normal response, some queries goes to NS2 and NS4, but opposite, comparing to the previous case, that we have less query that goes to NS2 and NS4 because the children state that also NS1 and NS3 is authoritative for this domain, is authoritative name server for this domain. Case of parent is a superset of the child. We have NS1 and NS3, and that is defined in the parent and in the parent and in the child, and NS2 and NS4 defined only in the parent. And what we have here is that most of the query goes obviously to NS2 and NS4 because it's preferred, because it's one of the parent, and only a small amount of query goes to NS1 and NS3. The REST experiment basically it's the case where NS1 where we define NS1 and NS3 only in the parent, NS2 and NS4 in the parent and in the child, and NS5 and NS6 only in the child. What we can see is that with the minimal response, resolver doesn't know the existence on NS5 and NS6, so they go only to NS1, NS3, and NS2, NS4. While in case of a normal response, they learn about the existence of NS5 and NS6, and they go also to this authoritative name server. So, which conclusion we can draw up from this experiment that basically having inconsistent NSSET in parent and child authoritative name server impact on how queries are distributed among name server. For all evaluated case, query will be unevenly distributed among authoritative servers, and the server listed at parent zone will receive more query than server specified in the child, and also that minimal response has an impact on the resolver's behavior. For this reason, we would also to evaluate in a static environment, in a closed environment, the resolver software behavior. In particular, we will pay attention to whether the resolvers follow the RFC 2181, which specify how the resolver should rank data in case of inconsistency. Which data the resolver should prefer. The RFC basically says that the child authoritative data should be preferred, but as we seen before, this is not always the case. We evaluate 4 popular DNS resolver implementation: bind, amount, not, and power DNS, and we evaluate also the Windows DNS resolver provided with Windows Server. We ran 4 tests. The first test, we ask for a simple A query to a subdomain of our test zone. In the second query, we ask for the NS record for our test domain. In the third query, we ask first for an A query and then for an NS query. This test aims basically to understand if the resolver uses non-authoritative information for answer to a direct query from the client. This is forbidden from RFC 2181. And in the fourth case, we try to invert this order. So we first do NS query and then do a query for understand if the resolver overwrite with the less authoritative information that come from the authoritative section of the A query, the authoritative information obtained with the first NS query. We discovered that not an amount complied completely with RFC 2181, so there is no problem in this case of these 2 resolvers. Bind packaged for Ubuntu Dainotti cache basically only information from the parent that does not override with the information from the child in case of the first case. So just use the information from the parent. This can explain some of the results that we get with dry pathless. But bind compiled for the source, so last version of bind basically in the first and third case perform an explicit NS query before performing any query without that user ask for this, and this basically helps because get information from the child before this information is more authoritative, so you get more authoritative information for resolving the query. And the last case is Power DNS, old version of Power DNS packaged for CentOS 6 and Ubuntu Xenial, and old version of Windows Server Windows Server Resolver use the cached non-authoritative information to answer to the NS query in the test number 3, and this is completely in violation with the RFC 2181. How we can solve this problem of parent-child inconsistency? One of the solutions is to implement the RFC 7477. RFC 7477 try to address this problem by introducing a method for automatically keep parent and child in sync, because basically the main problem here is that the parent and child zone usually are administered through different mechanisms. For editing, indeed for editing the parent zone, for example, of top level domain, we usually do that through the panel of configuration of the registrant registrar that basically are web interface, while the child zone are edited by modifying the zone file on authoritative name servers. This basically create this inconsistency. So this RFC propose a method for automatically keeping sync parent and child by polling periodically the child using SOA record, a new type of record called C-Sync. It's basically a mechanism similar to the child-to-parent synchronization for the NSSET DS records. Unfortunately, this RFC lacks of the deployment, but we strongly advise operators to take in consideration. And for conclude, we remember that the RFC 1034 that states that parent and child delegation should be consistent and remain so. It's basically one of the first RFC of the DNS. And either if this RFC should be implemented by everyone, we discover that a significant part of the namespace is misconfigured. And this obviously has consequences on the resolution process. So we strongly advise operators to verify their zone and to follow the RFC 1034 and to consider to implement these C-Sync DNS records. And we also want to recommend the resolver vendors to conform the authoritative information ranking in RFC 2181. With this I'm finished and ask you if you have any question, and I thank you for your attention.